Ahora está funcionando. Ah, vale. Y ahora sí. Ahora no. ¿Cómo? Ah, por aquí detrás. Vale. Muito obrigado, Varinha.
So we have now the second plenary talk of this morning session. It's by Cbiviaausina from Universidade Politécnica de Valencia in Spain. And we will talk about Cbiviaausina exponent and its relation with other analytic invariants.
Thank you very much. First of all, I would like to acknowledge the organizers of this workshop for the opportunity of giving a talk in this workshop, and also congratulations, Cbiviaausina. Well, I'm going to speak about Cbiviaausina exponents, and I am going to give an introduction concerning Cbiviaausina exponents that could last more or less 20-25 minutes. And well, first of all, I am going to, this is part of a joint work with Toshizumi Fukui, and in the first part of my talk, I am going to speak about a joint work with Santiago Encinas Carrion from Valladolid University also. So, let us fix a complex analytic function from Cn to Cn, such that 0 is isolated in the 0 set of G. Then we can consider the smallest of those alpha positive, such that there exists some open neighborhood of the origin and some constant C, such that this inequality holds in every point of the neighborhood U. So this number could be, the way this is defined, this could be any real number, but it is proven that this is a rational number. So this is a result of Cbiviaausina that this number does exist, right? And on the other hand, what is also possible to prove is that if we have two ideals, if I and J are two ideals of On such that V of J is contained in V of I, V of I contained in V of J, what we can also consider is the infimum of those alpha which are positive, such that the supremum of Hj of x to the power alpha is less than or equal to C, supremum of the absolute value of Jx for some constant. Yes, for all x belonging to some open neighborhood of the origin in Cn, where this is where we suppose that this Hj is a generating system, generating system of J, and these ones is a generating system of I. That is, we can do the same thing not only for complex analytic map germs from Cn to Cn, and we can also define this number in this much more general context. And these numbers seem to be, in some cases, they seem to be irrational, but they are always rational numbers. So this is how, I am going to give many results that are established in the context of a complex analytic map from Cn to Cn, but they can also generalized in this much more general context. So there is a very well-known result of Lejeune and Tessier that says that for a complex analytic map G from Cn to Cn, we have that the Cbiviaausina exponent of G is also a positive rational number. we also have that this infimum is actually a minimum. That is, there is some open neighborhood and some positive constant C, such this inequality holds for every point of U. On the other hand, we have a evaluative criterion to compute the weighted exponent of G. That is, the weighted exponent of G can be computed also as the supremum of the quotients of all orders when we compose G with complex analytic curves passing through the origin. And finally, which is the key point of our work, is that if we denote by I the ideal generated by the component functions of G, we always have that the weighted exponent is equal to the infimum of those P over Q, such that P and Q are integer positive numbers, and M to the power P is contained in the integral closure of I to the power Q. So we have here a link between an analytic concept, which is this one, which is this number that is defined as the minimum of those alphas, such that this analytic inequality holds in some open neighborhood of the origin. At the end, we have that this condition can be rephrased in terms of the notion of integral closure. This is a very deep result. So Teissier also proved that when we have a function f with an isolated singularity at the origin, and if we denote by R0 the degree of C0 determinacy of f, we always have that R0 is equal to the integer point of the weighted exponent of the Jacobian ideal plus 1. Right? And on the other hand, there is a known result of Bosky that says that if we have a map gem G from Cn0 to C0, such that G minus 1 of 0 is equal to 0, we have that the weighted exponent is upper bounded by the multiplicity of G, and equality holds if and only if the rank of the differential matrix is at least n minus 1. Right? If this inequality holds, if the weighted exponent of G is strictly less than the multiplicity of G, then we have that the multiplicity of G must be at least 4, and the weighted exponent of G must be at most the multiplicity minus 2. Well, what I'm going to do now is to give a connection between the to study what's going on between weighted exponent and weighted homogeneous filtrations. What I try to explain are many results in which, when we have a weighted homogeneous filtration, we can obtain very nice information about the weighted exponent. Let us consider a vector of weights W, and let us consider a polynomial f. Then we say that f is weighted homogeneous of degree d with respect to W when f is written as a sum of monomials of this kind. We have that every exponent k is in the plane which is determined by the weights, and belongs to this plane. Sorry. Let us fix a vector of weights that we will denote by W. So there is a lemma of Bosky that says that when we have a complex analytic map from Cn0 to Cn0, which is weighted homogeneous of degrees d1, dn with respect to this weighted homogeneous filtration, and if we suppose that this condition holds, then we have that the weighted exponent is upper bounded by the quotient of the maximum of the degrees over the minimum of the weights. So we have a first approximation between the weighted exponent and the information supplied by the weighted homogeneous filtration. Well, in particular, if f is a weighted homogeneous function with respect to the vector of weights W with an isolated singularity at the origin, we always have that the weighted exponent of the gradient of f is less than or equal to d minus the minimum of the weights over the minimum of the weights. So a natural question is when we can say that both numbers coincide. Well, one of the motivations of our work is the following result of Krasinski, Oleksik, and Posky that says that if we have a weighted homogeneous polynomial of degree d with respect to w with an isolated singularity, and if we denote that, if we denote by w0 the minimum of the weights, then when n equals 2 or 3, we have a formula for the Weierstrass exponent. This is given as the minimum between these two numbers. I mean, between the maximal bound for the Weierstrass exponent and the Milnor number. But this holds only when n is 2 or 3. Because in dimension 4, well, in dimension 4, we will see an example in which it is not true. Right? So in the case in which d is bigger than or equal to twice the weight, we will have that this is less than the Milnor number. And then we have that the Weierstrass exponent is the maximal possible value. Well, let us consider here a function which goes from C30 to C0, which is given by this expression. We observe that f is weighted homogeneous of degree 4 with respect to the weighted homogeneous filtration determined by this vector. And we have that the Milnor number is 1. And in this particular case, we have that the Weierstrass exponent is equal to 1, which is the minimum between 1 and 4 minus 1 over 1. So there is a result, as I told before, there is an example of Maciek-Sekalski that shows that in general, we cannot expect that this number is equal to the maximal one. So let us consider this function, which is given by this polynomial. We observe that f is weighted homogeneous of degree 15 with respect to this vector weights. This condition does not hold, and on the other hand, what we have is that the Weierstrass exponent is equal to 2. In this case, what we have is that the Milnor number is 4, and d minus the minimum of the weights over the minimum of the weights is 4. So we cannot expect that this formula is true in any dimensions. Well, what I show now is a result that shows an expression for the order of a semi-weighted homogeneous function with an isolated singularity at the origin. I mean, what is shown before are many results concerning the exact determination of the Weierstrass exponent when f is a weighted homogeneous function. And what I give here is an expression for the order. So you can imagine that in some sense I am surrounding the Zariski conjecture, right? So we have an exact formula for the order of a weighted homogeneous polynomial with an isolated singularity at the origin, and this is given by this formula. It is not still known if Weierstrass exponents are topological invariants or not, but we can do something for weighted homogeneous and when the dimension is 3, right? So there is a result of Osamu Saeki that says that if we have two weighted homogeneous polynomials of degree d with respect to some weighted homogeneous filtrations, and if we suppose this technical restriction, and if we suppose that the zero sets of f and g are homeomorphic as embedded surfaces, we have that both sets of reduced weights coincide. Well, I call a reduced weight the quotient between the degree and the weight. And this holds when dimension is 3. So the same result is also proven by Takashi Nishimura and Yoshinaga Suzuki in dimension 2. So in particular, what we have is under the same circumstances, we have that the Weierstrass exponent and the order must be the same. So when we have two weighted homogeneous functions from C3 to C with an isolated singularity at the origin, we have that since this set must be the same thing. And Krasinski proved that since we have by Krasinski, Oleksik, Plosky, we have that this is equal to the minimum, and under this technical condition, the Weizsäck's exponent must be equal to this number. Automatically, we have that under the conditions of Saekki's theorem, we automatically have that both the order and the Weizsäck must be equal. So, in particular, in dimension 2, we have these two formulas when d is bigger than or equal to twice the weight for all I. So we have that the Milnor number is equal to this expression by the Milnor-Orlik formula, and we have an expression for the Weizsäck exponent. Then in dimension 2, we have that the set of reduced weights can be also seen in this way. Right? So we have the following questions. If we fix a function f from C and 0 to C with an isolated singularity and which is weighted homogeneous of degree d with respect to W, is it true always that the Weizsäck exponent must be equal to d minus W0 over W0? Always. So this is a question that is not still solved. Only in dimension 2 and 3. And as I said before, when we have two functions with an isolated singularity at the origin, which are topologically equivalent, is it true in general that the Weizsäck exponent of f is equal to the Weizsäck exponent of g? In dimension 2, this is true. And Teixeira proved that. But in general, we have no answer. Only in dimension 3 and for weighted homogeneous functions. Right? I must say that this condition here, and this condition here for the point of view of the objective of computing the Weizsäck exponent of an arbitrary map, which is not a gradient map, is translated in this way. I mean, di is bigger than or equal to wj for all I and j. And in general, this is easy to find examples in which the Weizsäck exponent of g is not equal to this quotient. So this problem, we can say that is a characteristic of gradient maps. Well, on the other hand, if we have two weighted homogeneous maps with respect to the same weighted homogeneous filtration and with the same degrees, it is not true that they have the same Weizsäck exponent. They have the same multiplicity, but they do not need to have the same Weizsäck exponent. So our approach to Weizsäck exponents is purely algebraic. So in order to approach them, we must work with the notion of mixed multiplicities in the sense of Riesz and Riesler and Teixeira. So we have to define a notion of mixed multiplicity that must work even in the case in which each ideal do not have a finite colength. So one of the key points is to consider the sequence which is given by the mixed multiplicities I1 plus m to the power r, in plus m to the power r. I mean, what I do is to consider this family of ideals, and what we do is to sum powers of the maximal ideal. So this sequence is an increasing sequence, and for some families of ideals, this sequence stabilizes. So if we consider a Newtonian local ring of dimension n, then we define the Riesz mixed multiplicity of I1, In in this way. Let us consider the sigma of I1, In, which is defined as the maximum of the mixed multiplicities which are given by these expressions. Well, we remark that if each I sub I is an ideal of finite colength for all I, then we have that the Riesz mixed multiplicity, which is given by this expression, is equal to the usual one. Right? I must say, well, let us recall that if we consider many ideals, I1, In, if we consider here let I1, In ideals in On. So the mixed multiplicity ideals in On of finite colength. Then the mixed multiplicity E of I1, In can be also seen as the usual multiplicity of J1, Jn, where J1, Jn is a generic element in the direct sum I1, In. This can also be seen in this way by a result of Ries and Northcott. Well, sorry, by the result of Teissier. So the mixed multiplicities of many ideals that have finite length can be also seen as the usual multiplicity of a complete intersection ideal in which we take each Ji equal to a generic linear combination of some generating system of I sub I. And then we have that when we consider many n ideals in a Noetherian local ring of dimension d, such that the residue field is infinite, we have that the sigma of I1, In is finite if and only if we have some family of G1, Gn, which is a generic element here, such that sigma is equal to this multiplicity. So if we fix n ideals in a Noetherian local ring Rm such that the sigma is finite, we can define which is the minimum of the integers such that this multiplicity is equal to this one, right? So recall that sigma of I1, In sigma of I1, In is equal to the maximum. This is equal to the maximum of where R is bigger than or equal to 1 of the multiplicities EI1 plus m to the power R plus In plus m to the power R. So this is equal to the maximum, and we can have a look to which is the minimum of the R such that this multiplicity is equal to this one, or which is the point from which the sequence stabilizes. And we'll denote this integer by this way, R1, R of I1, In. Well, let us consider some ideals, some monomial ideals of On such that sigma of I1, In is finite. So I'm going to denote by S of I1, In. This is equal to the family of those maps G from Cn0 to Cn0, for which G minus 1 of 0 is equal to the origin, and Gi belongs to I sub I, and the Ries multiplicity is equal to the multiplicity of G1, Gn. Moreover, I'm going to define as S0 of I1, In, which is the set formed by the maps G1, Gn, that belongs to S I1, In. I mean, these are the same maps, but what we impose also is that the Newton polyhedron of Ji is equal to the Newton polyhedron of I sub I. So under these circumstances, we have, well, if we consider n monomial ideals in On such that the Ries multiplicity is finite, and if we consider any map G that belongs to S0 of I1, In, then the Weierstrass exponent of G only depends on the monomial ideals that we have fixed from the beginning, and this is given by this expression, right? So what we have given is a sufficient condition for a complex analytic map G1, for a complex analytic map G1, Gn belonging to I1, In to have the same Weierstrass exponent and depending only on the monomial ideals that we have fixed from the beginning. So this is the motivation for the definition of the Weierstrass exponent of n ideals in a Noetherian local ring of dimension n. So this is the motivation. And the definition is this one. If we fix n ideals in R, and we suppose that the risk multiplicity is finite, we have to impose this condition in order to guarantee that all the numbers, all the integer numbers that we have here exist. So when we consider the infimum of this sequence, well, we will call it the Weierstrass exponent of I1, In. So what I developed a couple of years ago is a method to compute effectively this number using singular. Well, we remark also that if we consider n ideals of On such that the risk multiplicity, well, in On or in any Noetherian local ring of dimension n, what we will have is that the Weierstrass exponent is between this number and the other number, and this number minus 1. Well, our approach to Weierstrass exponent allows to explain the lower semi-continuity of Weierstrass exponent. I mean, when we have any deformation, when we have an analytic family GT from Cn0 to Cn0, Cn0 such that 0 is isolated, j minus 1 T0 is equal to the origin for all t, when we have an analytic family, then the Weierstrass exponent is not lower semi-continuous, and this is also not lower semi-continuous. So we can have any behavior concerning the lower semi-continuity or the upper semi-continuity of Weierstrass exponent. But if we suppose that this deformation has constant multiplicity, this is lower semi-continuous. Right? So this is explained by the result in a much more general context. I mean, when we have a Noetherian local ring of dimension n, then for each I from 1 to n, we can consider two families of ideals, I sub I and j sub I, such that this is contained in this one. If we suppose that the risk multiplicity of I1, In is finite, and both have the same risk multiplicity, then we have that this is lower bounded by the other Weierstrass exponent. So it does not behave as a multiplicity. Because multiplicity, we know this is upper semi-continuous, but this is neither both of the two concepts, right? So there is an example which is due to Nemeti and McNeil, in which, well, what we have here is a family from C2 to C2, which is given by this expression. We have that 0 is isolated in the 0 set of each ft for all t. The multiplicity is constant, and the Weierstrass exponent when t is 0 is 8, and when t is not 0 is 16. Right? So I'm going to speak now about what could be said about the Weierstrass exponent when we fix a Newton filtration, not only in the weighted homogeneous case. And then I'm going to give the main result of Santiago Encinas and me, which is going to appear soon in Revista Matemática Complutense. So let us fix a coordinate system x1, xn in Cn, and we will denote the monomial x1, k1, xn, kn by x to the power k. So, well, as you know, if we consider an analytic function and we consider the Taylor expansion around the origin, we can define the support of H. This is equal to the set of those k such that ak is not 0. If H is not 0, the Newton polyhedron of H, which is denoted in this way, is the convex hull of this set. If H equals 0, then we fix the Newton polyhedron of H as the empty set. if we fix an ideal of On and G1, Gs is a generating system of I, then we define the Newton polyhedron of I as the convex hull of the union of the Newton polyhedra of some generating system of I. So this is very easy to check that this definition does not depend on the generating system of I. So let us fix a convenient Newton polyhedron, and what we can consider is the Newton filtration, which is determined by this Newton polyhedron. And we have to consider the family of vectors supporting some compact phase of dimension n-1 of gamma plus. Right? So we're going to define the filtration mapping in this way, and this is, you will find this in Kuznirenko's paper also. So we observed that the filtrating map, which is a map from Rn plus to Rn plus, which is defined in this rather technical way, this verifies that sends the integer lattice to the integer lattice. On the other one, what we have is that phi gamma is linear on each cone. I mean, when we fix a Newton polyhedron, we have that this map phi gamma is linear on each cone, right? So what we can have is something in this way. So we have here many cones. So this is when we fix a phase delta, when we fix any compact phase of maximal dimension delta, what we have is that this map is linear in this cone, right? And what we have also is that this map has the same value on the boundary of gamma. So if H belongs to On and H is not 0, we can define the new gamma of H, which is equal to the minimum of phi over gamma of phi gamma of K, where K varies in the support of H. And we say and we set nu of gamma of 0 equal to infinity. Well, we remarked that Newton filtration have rise to important graded algebras that are fundamental for the work of Kuznirenko about the determination of the Miller number of Newton non-degenerate function. Well, there is a result of myself with Fukui and Marcelo Saya that says that when we fix a Newton filtration and we consider many functions and we denote by R sub I, which is equal to the degree of GI with respect to the Newton filtration that we have fixed, and if we suppose that the ideal generated by these functions has finite colength, then we have that the multiplicity is Laber bounded by this number, and equality holds if and only if the system is non-degenerate on gamma plus. Well, I know I don't have enough time to give here the precise definition of what a non-degenerate system is, but this is a concept which is a rather straightforward generalization of the notion of Newton non-degenerate function. So the result shows that if we fix n ideals in On and we denote by Ri the value of the Newton filtration on each Ji, what we have is that the risk mix multiplicity is Laber bounded by this number. So we will say that this family of ideals is non-degenerate on gamma plus when equality holds here. I mean, when the risk mix multiplicity is the minimum possible value. Let us fix a convenient Newton polyhedron. So we can consider the Newton filtration. Well, in order to say something concerning the Weierstrass exponent, using the information of a given Newton filtration, we have to establish a notion of non-degeneracy that fits that fits together the information supplied by the Newton filtration and the ideal that we fixed from the beginning. So let us fix n ideals in On such the risk multiplicity is finite. And let us denote by Ri the value of the Newton filtration on each Ji. Let us denote by P the maximum of the values of the filtrations, and let A equal to the set of indices I, such that Ri is equal to the maximal possible value. Let us fix a proper ideal of On. Then we say that the pair is gamma plus linked, that the pair which is formed by I and the n ideals is gamma plus linked, when there exists some index in A such that this set of ideals is non-degenerate with respect to the Newton filtration. I mean, when we have many ideals in On, we have to look at the set of places in which we have maximal degree. So when we substitute in some of these places the ideal I, this set of ideals can have minimal multiplicity. So in this case, we say that the pair is gamma plus linked. So if we suppose that the set of ideals that we fix here are gamma plus linked, what we have is that this pair is gamma plus linked if and only if this relation holds, which is a rather technical question. So the main result says that, well, let us define by BR the ideal which is generated by the elements H such that the Newton filtration acting on H is at least R. So we have a family of ideals, and we have the following result that says that when we fix n ideals in On such that the risk mixed multiplicity is finite, and we suppose that Gn is non-degenerate with respect to the Newton filtration, and if we fix a proper ideal I, then we have that the Cbiviaausina exponent is less than or equal to this upper bound, which is completely analogous to the Krasicki-Oleksik-Plotski bound, and equality holds when the pair formed by I and G1, Gn is gamma plus linked. So this result works not only in dimension 2 and 3. So this is for all n. Right? So we have a tool. Well, the computation of Cbiviaausina exponent is not an easy task. So what we have here is a tool to estimate and to determine, in some case, which is the value of the Cbiviaausina exponent. Well, let us consider the following map from C30 to C30, which is given by this function with parameters, right? So we have that the Newton filtration is determined by this piecewise linear function. We have the set of degrees with respect to, the set of degrees with respect to the Newton polyhedron, which is given by G1, is equal to this set of numbers. And at the end, what we have is that the Cbiviaausina exponent of G1, G2, G3 is equal to 6a. Well, there is another result in which what we do is to particularize the previous results to gradient maps. So let us fix a weighted homogeneous filtration, and let us denote by W0 the minimum of the components of the vector W. Then we define AW, which is equal to the set of indices in which the minimum is attained, and we define MW, which is the set of those xi such that I belongs to AW. So given a function f and an integer I, we denote by sub I of f, which is the set of those k that belongs to the support of f, such that ki is not 0. So we observe that if I belongs to the set 1n, we have that this set is empty if and only if f does not depend on the variable xi, which never happens if f has an isolated singularity at the origin. So if we fix a semi-weighted homogeneous function of degree d with respect to w, and we denote by h the principal part of f with respect to this weighted homogeneous filtration, if we suppose that there exists some index in AW, which is one of the indices in which wi is equal to the minimum, such that this partial derivative belongs to mw, then we have that the weight-safety exponent of h, which is the principal part, is equal to the weight-safety exponent of f, which is equal to the maximal one. So, in particular, if we suppose that aw is equal to I0, which means that there is only one component of w in which we have the minimum value, and if k I0 is at least 2 for all k that belongs to this set, then we have equality here. I mean, if we are lucky and we have a vector which only one index in which we have the minimum between the components of f, and we have that this is true for all k belonging to sub I0 of f, then we have equality here. Well, for instance, we have a weighted homogeneous function from C30 to C0, well, with all these terms. The weighted homogeneity is given by the vector w equal to 1, 3, 1, 3, 4. Let us remark that this term has degree 13. So we have that the minimum is attained in 1, and we have that all the exponents of x are bigger than or equal to 2. So we have equality here. Well, there is another example here, which is rather complex. We have a function h from C4 to C, and we can apply these techniques, and we have that the weight-safety exponent is given by this expression. Well, this is all the introductory, all the things that I wanted to say concerning weight-safety exponents in general, and I'm going to approach the work that I have done with Toshizumi Fukui recently. Well, there is a result which is very well known that says that if we have a weighted homogeneous function with an isolated singularity at the origin, and we have an analytic deformation of f, if the Milnor number of the deformation is constant, then the order is also constant. So we have the following natural question. Is the same conclusion true for the weight-safety exponent? We don't know. Right? So this is a question that was posed by Bernard Tessier, and my impression is that it has the same complexity as the Zariski conjecture. I have to say also that when we have recall that we have defined the weight-safety exponent not only for complex analytic maps G from CN0 to C0, then we have defined also for pairs of ideals ij that contain in On, such that V of I is contained in V of J. So in this case, what we can consider is the supremum, the infimum, of those alpha which are positive, such that the supremum of Jx to the power alpha is less than or equal to C, the supremum of Jx for all x small enough. So we can speak about the weight-safety exponent of J with respect to I. So what I have to say also is that when we have a function f that belongs to On, the order of f can be seen as the weight-safety exponent of the maximal ideal with respect to f. So what we have is a restatement of Zariski's conjecture in terms of weight-safety exponents. So my impression is that the answer to this question has the same complexity as Zariski's conjecture. What we can prove is that if we fix a weighted homogeneous function of degree d with respect to the set of weights W with an isolated singularity at the origin, if we suppose that the weight-safety exponent of the gradient map of f is equal to this expression, which happens when n equals 2 or 3, and if we consider an analytic deformation of f, which is Milnor constant, then it's possible to prove that the Wesel's exponent is also constant. So we have a version of the Groyal-Cauchy result for the Wesel's exponent of a weighted homogeneous function. So I have to say also that there is a result that says that in Whitney equisingular deformation, the Wesel's exponent of the gradient must be constant. I mean, if we have an analytic deformation which is nu star constant, then the Wesel's exponent is also constant. But the key point is to prove that if we have a deformation which is Milnor constant, it is not still known if the Wesel's exponent is also constant. Well, what we have proven is that if we have two functions with an isolated singularity at the origin, then if f and g are by Lipschitz equivalent, we have that they have the same Wesel's exponent. And on the other hand, what is also possible to prove is that when we have two complex analytic maps with this condition, if f and g are by Lipschitz equivalent, they also have the same Wesel's exponent. So let me recall what is by Lipschitz equivalent. So these are rather well-known definitions, but I'm going to give some basic definitions. So let us fix a map from U to Kp, where K is the field of the real or the complex numbers. So we say that f is Lipschitz when we have this inequality for all pair of numbers xa, xy that belongs to U. So, on the other hand, we say that bijective maps between two open sets of Kn is a bi-Lipschitz map when f is Lipschitz and the inverse is also Lipschitz, which is the same thing as imposing this condition in some open neighborhood of the origin. So, if we have two function germs, two map germs, we say that f and g are by Lipschitz equivalent when there exists some germ of by Lipschitz homeomorphism phi from Kn to Kn, such that we have that f is equal to g composed with phi. Well, let us consider the following deformation, which is a map from C2 to C2. We have that ft is weighted homogeneous with respect to the set of weights w equal to 3, 1 of degree 9, 4. We have that this condition is true and that the Wesel's exponent of f0 is 4, and when t is not 0, the Wesel's exponent is equal to 9. So in this case, we have that this map is not, this deformation is not by Lipschitz trivial, right? So this is not by Lipschitz trivial. This is an example also, this is an example of the fact that when we have two maps which are weighted homogeneous with the same vector of degrees with respect to the set of vectors, with respect to the set of weights w, then they do not need to have the same Wesel's exponent. So this is an example of this fact. Well, there is a definition of a notion of by Lipschitz equivalence of two ideals, but I don't think that I have enough time. But well, I'm going to try. Let us consider two maps f and g from U to CR. Then we say that f and g are almost everywhere equivalent if there exists some matrix R times R's whose entries are functions from D to C defined in a dense set D which is contained in U, such that A of x is invertible for all x belonging to D, and the columns of both matrices A and A minus 1 are bounded in D. And we also have that G is equal to f of x multiplied by A of x for all x belonging to D, where we consider f and g as row vectors. If we consider two ideals of On, we say that I and j are by Lipschitz equivalent if there exists some R bigger than or equal to 1 and two families F1, FR, G1, JR of functions such that this is contained in I, the integral closure of F1, FR is equal to the integral closure of I, which is to say that this ideal is a reduction of I. We have the same thing for the other ideal, and there is a bilisted homeomorphism phi such that this map and this map are almost everywhere equivalent. So we have a notion of bilisted equivalent for two functions, and this is a generalization for two ideals. So this is an ad hoc generalization because by Rademacher's theorem, we have that for a bilisted homeomorphism, this is almost everywhere differentiable, and the differential is bounded whenever it exists. So what we were able to prove is that when we have two ideals, I and J, which have finite colength, if I and J are bilisted equivalent, then they have the same Weierstrass exponent. So, as I said before, by Rademacher's theorem, we have that if F and G are two complex analytic functions from Cn0 to C0 with an isolated singularity at the origin, what we have is that if F and G are bilifted, if F and G are bilifted, where we suppose that, well, this is F, this is G, and phi is a bilifted homeomorphism, automatically we have that, then we have that the ideal generated by the partial derivatives, I mean, the Jacobian ideal of F is bilifted equivalent to J of G, according to the previous definition. So in this case, what we were able to prove is that when we have two ideals of finite colength in ON, if I and J are bilifted equivalent, then they have the same Weierstrass exponent. What I'm going to define now is the sequence of mixed Weierstrass exponents. I mean, in the same way that we can define the nu star sequence, well, the nu star sequence is the sequence of Milnor numbers when we restrict the function to generic hyperplanes of different dimensions. So we can do the same thing for the Weierstrass exponents. So when we have an Noetherian local ring, and I is an M primary ideal of R, and we consider any proper ideal J of R, we define the ith relative Weierstrass exponent of I with respect to J in this way, right? So this is the Weierstrass exponent of I copies of I with M copies of I. Well, recall that we have defined in the previous slides a definition of what is the meaning of LJI1 IN in a very general context, I mean, in a context of any Noetherian local ring. So in this, we are especially interested in the case in which J is equal to the maximal ideal. So this vector has remarkable properties. One of them is that this number can be seen as the Weierstrass exponent in the usual sense of the restriction of the ideal to generic hyperplanes. And on the other hand, what we have here is an increasing sequence. So for any ideal that has finite colength, we have the increasing sequence of Weierstrass exponents. So if I has finite colength, or in primary, in Rm, what we have is that we have automatically the sequence of mixed Weierstrass exponents. L1, L2, Ln. And this is always equal to the order of the ideal, the order of I, which is equal to the maximum of those R, such that I belongs to M to the power R. So the first one is the order. Right? Oh, this is written here. Right. When we have a Noetherian local ring and we consider two families of M primary ideals in R, what we have is a relation between the sequence of mixed Weierstrass exponent and the quotient of the Riesz mixed multiplicities, which is given by this expression, right? This is given by this rather technical expression, but in the very particular case in which we have that all the ideals I1, In coincide to some ideal I, and we consider the case in which each of the ideals J1, Jn are equal to the maximal ideal, we have that the multiplicity of I is upper bounded by the product of the mixed Weierstrass exponents, which is a very nice thing, right? So you can see this relation in a recent paper also of Hickel. I think it's a Journal of Pure and Applied Algebra, recently. So what he does is to give the definition in the very particular case in which we have an ideal of finite colength, and we consider Weierstrass exponent with respect to the maximal ideal. So at the end we have that the summary multiplicity of I is lower bounded by this, is upper bounded by this product. So in the particular case in which we consider a function with an isolated singularity at the origin, we have that the mean Lord number is less than or equal to the product of the mixed Weierstrass exponents. So one natural question is, when equality holds, right? So we conjecture, well, in fact, Hickel gives a proof in dimension 2 of the fact that when we consider an ideal I, when we consider I which is contained in On of finite colength, well, we have that the multiplicity of I is less than or equal to the product I1 to the n Li O0. So we conjecture that equality holds, if and only if there exists some Q bigger than or equal to 1, such that the integral closure of IQ is equal to the integral closure of J1, Jn, such that this belongs to On, and the principal parts with respect to the maximal ideal, Pj of -1 of 0 is equal to the origin, right? So this P means the principal part with respect to usual order. Principal part with respect to M-adic filtration. So in dimension 2, it is clear, but in general not. It is not clear. I have tried many times, and there is no way at this moment, right? Well, another question is, when we have a monomial ideal, is it easy to find the sequence of mixed Weierstrass exponents? So the answer is yes, and it is given by this formula. So in particular, when we, well, as an example, if we consider the ideal generated by these elements, where A, B, and C are at least 10, we have that the sequence of mixed Weierstrass exponent is equal to these three numbers. And what we have to say is that the L2 does not depend on A, B, and C, which is somewhat surprising. Well, let us fix a deformation Ft from Cn0 to C, and let us suppose that Ft has an isolated singularity for all t. If Ft is a bi-Lipschitz trivial deformation, is it true that the sequence of mixed Weierstrass exponents is constant? Well, for the order, which is the first one, and for the usual Weierstrass exponent, it is true. But what's happening in the middle? What's happening in the middle for the sequence of mixed Weierstrass exponents? Well, there is a technical result that allowed us to compute Weierstrass exponents. Well, the difficult part is to compute when n equals 3. One of the difficult parts is to compute the L2 of Ft. in a deformation, gradient of ft. So this is the difficult part, and we took advantage of the following result of Bernard Teissier. I don't have enough time to explain it in detail, but what I want to show to you is what's going on with Brianson's better example. If we consider this family, this is very well known that ft has an isolated singularitY at the origin for all t. It is not so well known that the integral closure of the Jacobian ideal is a monomial ideal, which is the same as saying that the J of f0 is Newton non-degenerate. This is not Newton non-degenerate, and this is the reason that we have to take advantage of the previous Teissier's result. We have that ft is weighted homogeneous with respect to this set of weights and with of this degree. The new star is not constant, which is something which is very well known, but this is new constant, but the sequence of mixed Weierstrass exponent, they are not constant too, right? But the deformation is not by Lifshitz, which is something that, if I'm not wrong, was proven by Lev, Alexander Fernandez too, and Satoshi Koike also. Right? So what we have is that the sequence of mixed Weierstrass exponent is 5, 7, 14 when t is 0, and when t is not 0, drops. The second one drops. And another example, which is by Artal, Fernández Bobadilla, Luengo, and Meyer, which is another example of a deformation which is not new star constant, is new constant, but in this particular case, we have that the sequence of mixed Weierstrass exponents is constant. So it is not still known if the L star vector is by Lifshitz or not. So, well, to end, I wanted to explain some things related with the notion of low canonical thresholds, but we don't have enough time. So thank you very much. Thank you very much.
If you assume that F is homogeneous, which is stronger than weighted homogeneous, do you have the result about the Weierstrass exponent being equal to the minimum of the Milnor number and the weight expression that you had on the board?
No. In
No,
this case,
so it doesn't work. So the example you gave, counterexample you gave, was one where it was weighted homogeneous but not homogeneous. So even if you assume it's homogeneous, it doesn't work.
homogeneous. Well, in this case, what we have is that if we fix a function which is homogeneous with an isolated singularity, homogeneous, we have that the Weierstrass exponent of degree d, we have that the Weierstrass exponent is equal to d minus 1. Nothing more.
That's no problem, right? Okay.
Always.
Yeah. Now,
It's always true.
the other question I had was, can you do anything in higher codimension? You'd have to change your...
Sorry?
Can you do anything in higher codimension? You've been looking at functions for much of the talk. How about complete intersections with isolated singularities? So you'd have to change your setup a lot, but I was wondering if you thought about it.
Well, the notion of Weierstrass exponent can be given in much more general context. So
Yeah.
I think that something new could be said in the context of isolated complete intersection singularities.
Okay.
Any other question, comment? So let's thank the speaker.